These effects were made in Godot, the hottest open source game engine on the scene right now, which boasts shader tools that, on the surface, are pretty similar to Unity's. But how does it stack up to Unity? Join me for this tutorial/opinion piece where I try out Godot's visual shaders for the first time and see what I love and hate about everyone's favourite free game engine. As a total beginner, my first stumble was adding a test sphere to my scene because I kept adding a CSG sphere from the node list, when instead you're meant to add a mesh instance 3D and then pick a sphere mesh from the mesh list. Much better. In Unity you have the concept of scenes and prefabs, but in Godot we just have scenes. And then you can drag scenes into other scenes. So for each shader I worked on, I made a new scene, added a sphere or another mesh to those scenes. These are like Unity prefabs. And then I have one master scene containing an instance of each of those other scenes. Here's your fair warning that I'll probably be comparing stuff to Unity a lot because that's what I'm used to, and spoiler alert, here are the shaders I made. I'll be talking about these three in the video. Oh, and I'm using Godot 4.2.1. I figured the best way to go about this would be to recreate shaders I've already made for Unity, so I started with a dissolve shader. The premise of the dissolve effect is simple. Cut off parts of the material based on its height in world space. Add a bit of noise to modulate the shape of the edges, and maybe make the edges glow. I like this example because it's simple, but it touches on quite a few shader topics. I created a new shader material here on my sphere in the geometry dropdown, and then when I click on the material, I can attach a new shader. I'll choose visual shader as the type and name it dissolve. And here we have Godot's visual shader editor. It's a lot like Unity's. In the middle we have the graph outputs, although pretty much everything you'll ever need is here from the start, and I'm not sure if there's a way to hide any of them. Unlike Unity, you declare properties in the middle of the graph, so let's right-click to bring up the Add Node window and find color parameter in the list. We can rename it by typing whatever we want in this box, but it will filter out special characters and replace white space with underscores. We can also choose to give it a default value using this tick box, otherwise Godot uses a sensible default for each type, such as colors being white. I'm going to name this property base color and connect it to the albedo output, which you can think of as the basic color of the object before lighting is applied. Now let's do the height-based cutoff. To do this, we'll need to connect something to the alpha output and something else to the alpha scissor threshold. Every pixel whose alpha value is lower than the alpha scissor threshold will get culled. I'll add a flow constant to the graph, set it to a value of 0.5 and connect it to the alpha scissor threshold. Then we'll right-click to add a node for the world position of the current pixel, and there isn't one. These ones don't quite do what we want. For example, node position world gets the pivot position for the object as a whole. We have to set this up ourselves, which is a shame because I use world space position rather frequently in my shaders. Using this drop-down in the top left, I can swap the graph view from fragment mode, which operates on each pixel, to vertex mode, which operates on the vertices of the mesh. This section of the graph lets us do stuff like animate the shape of the mesh, but we'll use it to calculate the world position and just pass it along to the fragment stage. It's efficient to do it here because there are typically many more pixels than vertices covered by a mesh. In shader terminology, this kind of data is called varying. If we click on the Manage Varyings button and then Add Varying, let's create a vector 3 called WorldPos. Now we can add a varying setter node to the graph and find our WorldPos varying from the drop-down list. This is basically an extra output. To calculate the world position, we need to get the object space position of the vertex through the aptly named vertex input node and multiply it with the model matrix, which is the transformation which changes positions defined relative to the mesh itself into positions defined relative to the world the mesh exists in, so in our case, a scene. To actually do that multiplication, there's a node called transform vector mult. Then we connect the output to the WorldPos varying we created. Look, I know I can't compare everything to Unity, but world position is just one node in Unity. The workflow here in Godot's visual shaders is a lot closer to how code-based shaders work, where you do indeed need to calculate all this manually in the vertex shader. But I feel like these graph tools also take a bit of this work out, you know? Anyway, head back to the fragment section of the graph, add a variant getter node to get our world pos, click the tiny arrow here to split the vector into its components, and then drag the Y component into the alpha output. The node says RGB, but it corresponds to XYZ. Then, after you discover this causes a bug in the Godot version I was using, instead, you close up the arrow and drag the whole vector into a vector 3 decompose node, and take the Y component from that instead. It's doing the same thing, so I'm not sure why the other approach was bugged. Oh well, hopefully it's fixed in the future. For this setup, Godot will cut off all pixels whose Y position is below 0.5. Let's make this a bit more customizable. I'm going to add another float parameter and name it dissolve height, which is going to be the height at which pixels get culled. Then I will add a node called step, and connect my new dissolve height parameter to the edge slot and the Y position into the X slot. What the step node does is compare the two outputs, and if X is higher than edge, it outputs 1, otherwise it outputs 0. What we're doing here is saying output 1 if the pixel is higher than the dissolve height. I want my dissolve to work in the opposite direction, so I'm going to use a 1- node to reverse the output and connect it to alpha. If I look at my test scene, we can see the changes being applied already. Since part of the object has been cut away, it looks really strange because we can't see the inside by default. To enable two-sided rendering, you need to click on the shader here in the inspector, then expand modes and change cull to disabled. You'll only see the outer shell of the object, but it's a damn sight better than seeing nothing on the insides. That's the easy bit. Now let's add some noise to change the shape of the edges. This is where I discovered a bit of a double-edged sword with regards to Godot, because there's no built-in node that just gets you some noise values, which was initially disappointing, but then I found out you can define your own custom nodes. Whereas in Unity, the best you've got is creating a custom function node, in Godot we can do something similar with the visual shader node custom class, but I think this is more powerful. Basically, we can write a script that extends the visual shader node custom class, give it an @tool attribute, which makes it run within the editor, then overload a bunch of functions that determine the name of the node and what its behavior, inputs, and outputs are. In fact, it can inject totally custom GLSL code into several places. Get code inserts code wherever you place the node. That's the one you have to define, and it's the one I expected to see. Get func code inserts code at the start of the shader stage, so if you add the node anywhere in the fragment stage, this code runs before anything else in the fragment stage. And get global code is super useful as it inserts code at the top of the shader file, so you can use this for helper functions and variables. And I love this. It's something Unity sort of can't do without hacks, I think. And then you can reuse this node in as many graphs as you want through the same node search bar as the built-in nodes. This makes it easy to create your own library of shader nodes that you can slot into any project you want. Luckily for me, there's a Godot docs page that outlines exactly how to set up a Perlin Noise 3D node. Unity's built-in noise nodes only operate in 2D, so this is fantastic. I won't go into detail about how the Perlin noise code works, because that's a whole video in and of itself. Just to know that it generates grayscale cloud-looking values using some input value as a seed. This node calls the input UV because it's commonly applied like a texture, but you don't need to use a UV coordinate as input. In fact, we won't be. This implementation also takes handy offset, scale, and time inputs, but we're only going to make use of scale. I'll input a float constant equal to 0 to the offset and time values. For the UV, I'm going to use world pos using the variant getter node from earlier, the full vector, not just the Y component. For the scale, I'll use a new float parameter called noise size. The resulting value from the node is the float between 0 and 1. I want the noise to act as an extra height offset, and I want it to be customizable, so I'm going to remap its values. I'll add another float parameter called noise scale, then use these following nodes to remap the 0 to 1 range to negative noise scale to positive noise scale. I can then add the result to the Y component of the height. Looking at my test scene now and playing around with the new parameters, we can change the shape of the dissolve quite a lot. The last thing I want to add is an emissive glow around the edges left after the cutoff. To see the glow, I'm going to head to my main scene which houses all of my shaders, click on the camera, add a new environment if it doesn't have one, and make sure the glow option is enabled. With that out of the way, let's return to the graph. I'm going to add one more flow parameter called glow thickness, which I'll give a default value of 0.05, since we just want it to be a thin edge. I will subtract this from the dissolve height parameter we previously added. This was a second cutoff threshold, so I will add a second step node just below the first one, then pass the new threshold into the edge slot, and pass the noisy Y component from before to the X slot. If we used this for the alpha output, we can see that this shape is almost the inverse of what we had, except there's a small bit of overlap. Multiplying the two together gets us only a thin lip around the edge. I'll just put that back to how it was. Using this value, I will add a final color parameter called edge color. For its default value, I'll make it blue, but I will make sure to swap to the raw tab and elevate the color sliders to values exceeding 1 as this produces a glow. Finally, we can multiply the mask and the edge color together, make sure that you use a vector op node, and output the results to emission. The graph is now complete. Next up on the docket is a simple hologram effect where scanlines scroll down the object and Fresnel light brightens up the outer parts. The scanlines will be driven by a texture, this texture to be specific. On a new visual shader, I'm going to add a node called texture2D which reads texture data and outputs a color. There are different options for reading a texture, so I'm going to pick sampler port, which reads whatever texture we slot into the sampler input. For that, I'll create a texture2D parameter so that we can swap out the scanline texture with a different one if we want. I'll name it scanline texture. I'll also add a color parameter called scanline color which defines the tint color for just the scanlines. I'll use a separate color for the Fresnel later. I'll multiply the texture and color together, then output the color to emission and just the alpha component to the alpha graph output. What we have so far isn't super interesting because the texture's just mapped to the surface of the object. I want to scroll downwards over time from top to bottom, so we'll need to change the UVs we use for the texture2D node. I'll give myself plenty of space to work with, then add a float parameter and name it scanline scroll speed. You can guess what this controls. I will also add a time node which gives us the number of seconds, I think since the game started. Let's multiply them together, and now we have a timing mechanism. Next, we're going to work on the scrolling from top to bottom. I want to do this based on the object's world space height, but you'll remember from the dissolve shader that there's no built-in node for that, so once again, let's go to the vertex stage, add a variant called world pos, input the model matrix times the vertex using a transform vector mult node, and then on the fragment stage we can use a variant getter and a vector decompose to get the Y component of the world pos. Let's add a float parameter called scanline scale and multiply it with that Y component. This will let us control how closely packed the scanlines are. The last step is to add this value to the timing mechanism we added previously, and then create a new vector2 using the vector compose node and slot our value into Y. The X slot can use whatever value we want because my scanline texture doesn't change horizontally. This gives us a new set of UVs we can use for the texture2D node. All that's left is to add the Fresnel light. Luckily, there's a built-in Fresnel node which works very similar to Unity's. We can slot in a power value to scale the size of the Fresnel effect. The higher the input, the smaller the Fresnel effect. For that, I'll add a float parameter called Fresnel power. Let's multiply it by a color parameter called Fresnel color. Remember that we can go to the raw tab in the color picker to choose high intensity colors. Now, setting up the final graph outputs is a simple case of multiplying the scanline and Fresnel values together and slotting it into the emission output, then multiplying their alpha values together and slotting that into the alpha output. This graph is also now complete. This video is getting pretty long, so it's a good job I left the simplest graph till last. Inverted hull outlines are a very basic method for adding outlines to objects, where you expand the mesh itself slightly in the vertex shader and color the entire object one color in the fragment shader, then render only its back faces. Then you render the object normally a second time and it'll render over the expanded inverted mesh. I'll jump straight over to the vertex tab of the graph and add a float parameter called outline size. We want it to be fairly small, like 0.05 maybe. I'm going to multiply this by the normal vector using a normal node, which gives us an offset value for moving the position of the vertex. Then I'll add the result to a vertex node, which has the effect of expanding the mesh. This can be slotted into the vertex output. It's probably worth noting here that the inputs and outputs named vertex here refer to the vertex position. Over in the fragment stage of the graph, all I will do is create a color parameter called base color and output it to the albedo. And that's it, the graph is complete. Although we're not actually inverting the hull yet, just expanding it, so we're rendering a slightly bigger sphere. In the inspector, I'm actually going to give my sphere a new standard material, which is essentially the same as Unity's standard lit material. This is the normal rendering of the object. If we expand the material by clicking it, one of the options is called Next Pass, which lets us attach a second material. This is where I'll add a new shader material and use my hull outline shader. Click on the shader field and make sure that under Modes, the cull option is set to front. That means the front faces will get removed and only the back faces are rendered, thereby inverting the hull like we wanted. And that's the outline vector completed. This was my first real attempt at making something in Godot. The process is surprisingly similar to using Unity shader graph for the most part, but with obvious differences that will take some time to get used to. For one, when you type multiply into the search bar, there are 7 different nodes with exactly the same name, which output different types. In Unity there's just one, and it can contextually figure out what output you want given its inputs. Plus it can take matrices, but in Godot you need a transform op to multiply with other matrices, or transform vector mult to multiply with vectors. And then there was the thing with getting world possessions. But it's not all frustrations. I'm pleasantly surprised by how fast Godot is with things like compiling scripts, and for that matter, GDScript seems alright, although I haven't used it much so far. I'm definitely gonna need to sit down and work with Godot a bit further, but I'm excited to make more videos in the future that focus on Godot, so make sure you subscribe to see more. Until next time, have fun making shaders.